Hello there. Welcome to part 2 of tutorial number 59. And I'm trying desperately to think of a place to start. And just by accident, sort of, I found exactly the right place to start. Because I'm in a situation here that doesn't make sense. Now, this program... Remember before I said that this type ID came from a totally different spot, right? And malloc was always a different type of address. And it's these addresses that I've been trying to make sense of the past few hours. And here again, PC has come back with a weird number. But so does malloc. Now, I did a dump in, partial dump in the program. It's the program running right now. It says it's program name somewhere. Here. Test run, test 1. Yeah, I did this dump prior to running the program. So this is the current running image we're going to dump in. And I'm looking through these sections. Now, I should have realized before immediately what those pointers were. These 4010 whatever. That's always code. The code always starts at around 4,100. 401,000, I guess, if you want. Hex. And the base address of all these things is always 400,000 hex. Always. See? Image base. 400,000. Now this number is below the base address of the image, which doesn't make any sense to me. Other areas that we were seeing are like this 46 something. Okay, now 46 things, 46 type things are like these numbers, these tables, which I've now turned into an array and trying to make sense of the derived class and base. Now that's not in this area. This area, that's 46C. 46, okay, so that's D, C and D are between this range. And that's read-only initialized data. Okay, so it's data, not executable. Which makes sense. Okay, so these are essentially like statics. This would be the same area where a string would be like a string literal would be in the same area. I don't know if I can find one in there. Let's do 46 CF94. Okay, now you see all these things are, here's the beginning, C4 or C00 is not visible here, but all of these things are definitely strings. Those mangled function names. And here's one that has to do with one of those debug traces. And I guess that's the end of it. I won't go out any further. At least If there's any more, hasn't been mapped into memory yet. So that those numbers make sense. There's 48 here. Now I've declared this table as a static member of the base class. Alright, now this goes up to 48 too. So there, it's in this area. That's just regular read-write data. Okay, so I could overwrite if I wanted to the value of this G tables, but not the things it points to. Okay, now this is 48, also initialized data, but it's got an I, 48.3, which is not this one. I don't have anything in that area, not that I can see immediately. Okay, now here's another one, 48.4, read only, something called rsource. I have no idea what, no idea what that is. Flags. I'm not sure what these flags, how to read the flags. C probably has to do with read write. Yeah. Okay. So what is C? C is the is 10, well that's 12. So that means that the top bit of these flags, when that's on, makes something read write, and when it's off, it's read only, probably. That's a full D-word with flags. And that's it. Well, there's text, that's the regular code. And we saw that. They're all based in for something. So it's a real mystery. I don't know what this area is. Let's write one down. 2759 Apple. Oh, and the stack's not showing up in here. I'm not doing enough. Maybe enough. Dump in. What else can I do? I know this seems like a diversion. I'm quite curious. Range, section. What I want is all sections. Oh, it could be anything. No. I don't know what this is. I could do all. Try to make sense of the all part. Alright, here's everything. Now, let's see. This magic number thing, something to do with DOS, believe it or not. Okay, I don't know what that is. I'm more interested in virtual address. I can search for that word. 46, 47, 48, 40. That's it. There's nothing there's no 2000 something. And there's no stack. Wait, this says stack. Size of stack reserve. Now see the stack. You'll notice that all these have the same segment number except for code. Now these don't necessarily, well, these definitely, well, these three are the same, so it doesn't matter. But these don't necessarily have to do with address. The segment thing just has like different flags and things in it. So this doesn't really say anything, unfortunately. Raw data, 40 something something something. Okay, well, the only thing it could possibly be, and unfortunately I haven't printed it yet, is an import of like a DLL or something. Okay, now this is freed memory here. I know that. FE, and it starts with 20. Am I reading these numbers wrong? There are 6 digits. 6 digits. Well, that's base. That's that string. But see, I did a P void malloc, which came from F0. Right. I'm going to copy this number. Use the same section, definitely. And it won't let me go up past this. And that starts there. It really makes very little, almost no sense. It's like it created this one on the fly. That's possible. You can create mappings. You can map things at arbitrary addresses. Like it could correspond as well to one of these addresses. Like, I wonder if I search for that word. That would be interesting. Oh no, it's. I don't see that tag. Oh, it wouldn't be. That was malloc. Wait a minute. It's got to be in this here somewhere else. Great name for my class. Oh, unrelated. Okay. Now I haven't called this function yet, so that could help. Oops. Right in there. Okay, let's see what happens. Oh, now I can show you how the code works. Number of functions. Okay, now that's in a something, okay, and it turns out, in this case, it's a base, object of type base, okay. Alright, so now this is a reference. If you recall, references and pointers are handled in exactly the same way. Okay, so you can just think of B here as a pointer to B, pointer to a base. Alright, so now to do this in assembler, first I want to get the address where this is stored on the stack. So that's what I usually use, load effective address. Now this should return a pointer in EAX stack, and that's definitely stack. Well, let me see it here. Address of B. Yep, EE4. No, 1, 2. So see, we haven't retrieved the address of B yet. We have this, but after the next line, that ECX should give us the address of B itself. One is the address where the pointer to B is stored, and now there it is, FEE4. So this truly is a pointer to a B on the stack. Otherwise, the first thing would have given us B, right? Remove the brackets, we would have got B. Okay, or something like that anyway. I'm saying that is this pointer of the object, and it certainly is. Okay, right. That's what my comment here means. A star of a B ref, right, gives you the address of this B, which is the address where this pointer is on the stack. Star it again, and you get this. Now star that again, and I'll get this V table, or DX. That's a 46 thing, which is we just saw, are those V tables. This particular one is the base one. Okay, now I start at 0, and I'm just walking through the table. Back to memory, to numbers that make sense. 46CF94. Okay. Now all these tables I found out are null terminated. So each one points to a function. Each element here points to a function, and it's null terminated. So if you want to find out how many there are, you just step through, advancing 4 each time till you hit 0. And that's all I'm doing here. Taking the EDX, adding 4 times some number, and as soon as I get a 0, I quit. Otherwise, increment to a number. So this is going up. These values here are functions. 41, right? 41. Here, that's this, maybe this one. 40107. No, this is 41. Well, which one do we want? 3. That's the last one. Oh, it's not showing it. Oh, that's probably what. Maybe that's why everything looked funny. It wasn't showing it in hex. No. Okay, anyway. Now it makes sense. 401078. That's here. And there should be the last one, 40107B. And so this will be 0 down. Save that off into return value. Trace that to the result. For virtual functions, return, and that's how I get the number of functions. Calling them is just a matter of calling the pointer in the table. And yeah, these still don't make sense. So to call one of those functions, suppose I want to call derives zeroth function. Oops, it's not right. I will call defunct, which takes a reference, which is a pointer, d 0. First, I step in here. Now, I had a mistake last time. I had a minus sign here, which is fixed. So now I simply want to locate that same spot. But since it's a member function that I'm calling, I need to put into CX the address of this pointer. A stack pointer, it turns out, but whatever. So that has to remain in CX. Now DX here, that's taking star of this, which is giving me the virtual function table. Then I want the index value of 0 in this case. Dx then contains the address of the function. And I didn't need to recompute it, but I recomputed it just to emphasize how to compute the address. And then it's a call. Now you'll notice, I should have put it in okay, we're in the right function. And this pointer is correct, right? That's our value, and everything's fine. Now, I should have put this into disassembly mode. I'll do that this time when we get to the right spot. Because I just want to show you the way it calls it. Get to the call. Alright, now I'm going to, instead of stepping, well, now it's in disassembly mode, so you'll see what happens. I should have recognized this immediately before. Remember, I was trying to find out what was address. Was that something E9? Everything was E9. Now I should have. It's my own fault. I should have realized right away because I've been typing these E9s in all over the place in the assembler stuff, which is a junk, right? And that's why these ones were always 5 bytes long. It's junk relative address, right? So now this just jumps to some other spot, and that's how you get there. So anyway, it all makes sense. And now if I want to call any virtual function, if I want to call any virtual function of type void, taking no parameters, I can use this thing to do function 4. Now it turns out that in this case, I added an extra function, so it derives the vtable contains more functions. That's 5 functions, whereas the base happens to have 3. So index 4 is the 5th function. 7? No, I don't know if I can figure it out yet. What I am printing out here are the virtual function tables as they come up, and trying to erase them as they go away. Okay. Now this should succeed. Yeah, it did. And that takes me to this particular function. Okay. Now, unfortunately, you can't tell, and there's no way to tell. In fact, it wasn't a problem. I thought there was a problem with the debugger when I was doing this last time, but it only ever lists 4, at most 4 functions, because I guess somehow this is declared as an array of size 4. This B pointer thing for base, and it never shows me derived version of this. I have it here listed, but I can never get that list in this watch window anywhere, unfortunately. So I can't. All I can do is compare. I can't compare my result with what it's supposed to be. Obviously, it's correct. Whoops. This. Well, that's what I was just looking at. It only gives base. And if you do address of this or something, doesn't work here. But if I go out of this, it looks like you could get it by doing this. No, not here. Somewhere. Oh, Sometimes it shows you a thing in square brackets here. But I don't see it. Maybe it would work if I start over again and don't go in there. Oh, no. Or maybe in food here. I'll have to make this a reference. That might be the reason why. That's true. That might be the reason why it puts that thing in square brackets in each case. Because supposedly you don't know. It's hard to tell. Yeah, there it is. See? Now that was the thing I was expecting to show up before, and I thought it would show me the table for a derived, but it doesn't. See, it just gives you the base again, and then you get only the first 4 entries, which have been modified. And say just as we were doing. It's not the right table, right? This table has 5 entries, but it can't figure out that there's more entries than it originally had, because somehow the declaration of this must be declared as a static array. In fact, it's in a 46 something section, which was here. 46 something is read only 46D. That's in there. So that's read only initialized data, and that's where you declare things like static data that doesn't change. You know, these can never be modified, right? So it's just impossible to get a printout. All right. Anyway, enough of that. The point was, I just wanted to see how it's implemented. It turns out it's implemented in exactly the same way that we expected. Every object gets its own virtual function table. Somehow or other, the table each object has a pointer to its current table, and somehow that pointer is modified. Now that maybe it's probably too late. Well, maybe quickly, if I just make that a copy, we might see in the disassembly how it restores that read table. I want to put a break. I don't have a copy constructor in base. It's just a regular constructor. These reports are just to print things out, but they do an update address thing. Well, last time this didn't get called, I don't think. I'll try that again. Let's see what happens. Okay, I expected that. Okay. Now, I'm just going to press F8. Now, it hasn't gone to that constructor. B here, table has been restored. So there must be a copy constructor involved. We'll try this again and disassemble it. Take the address of D, push it on the stack, call. Now see this here. This is not the default constructor. This must be the special copy constructor. See, this is not my code. I didn't write this. Here, and look, it's loading the offset of the bases retain. It's exactly what we did, right? It's restoring. I don't know what that stands for, but this and that. Maybe get rid of the symbol name. Okay, that is a plus. That is a plus, and this is a. Yeah, that is a. They called the thing passed in that, and they're calling the regular thing this pointer this, and they're replacing that stuff with this stuff with that stuff. Now, if that was passed in on the stack, oh, because it's a copy, right. Okay, copy has two. See, a copy constructor has two arguments, right? It has this pointer, which is going to be from CX, always CX, and that's at a that appears as though it's a local variable in the function because it goes in an EBP minus something. And then there's a thing being assigned, right? And so that would end up being pushed. And that was secretly pushed, if you recall. So in fact, these two start out kind of equal. Yeah, that's it. EDX is going to be that. 12EB4, and this here was pushed. Yeah, well, in any case, it's taking this virtual function table, the offset of that, and moved it into what was pointed at by EAX, which is this. Then that's the actual this pointer of the object. So it's replaced the function, regular function table. And if we step out of this, the magic copy constructor has been called. And oh, I can step too far out. Didn't I? Oh no. Oh yeah, I've stepped all the way back here out of the program. Exactly 100% as suspected. A copy constructor, it gets created and invoked when a function call happens, which restores the pointer, which creates a new object with the correct lead table. So there's no magic going on here. It's just what we thought. All right. So that's a brief introduction to virtual functions. Probably the longest you'll ever run across. One of the things I've done with this before I go, and I want to go through this next time. Silence, that's silence, quiet, and noisy. You might find this kind of cute. For the output. Let's see if that's what I want. Oh, I don't have this one. That's true. I want to copy that. It's going to be similar to when we do print out like this, but it's not do print out. It's going to be like the other. Oh, I see. No, this took us. What did it take us? String? Sorry about this. I added a macro. I can get rid of it. No, I definitely want that. I just need to define an attribute here, and then use string. Okay, almost there. And that's the regular. No, I can use this print format. No. I use this. do print out AT. Yeah, that might work. See, because I couldn't keep track with all the output. I couldn't keep track of what was going on. And so, what I did was I gave each class a color. And so, see, so the different classes have colors, and that way I can see which class is calling which function. But for the global things, they don't have an associated class, so I needed a way to indicate that as well. So those ones are these ones that show up with a background color, and their colors tell you that indicate that from which base they were. They're derived, but they could be called from anything. They don't require this pointer. And here you'll see there's a white thing and there's a yellow thing. And I have two objects. One's a white object and one's a yellow object. If I had three things, I would get three colors for the instances. And there they are, see? So it makes it easier to tell which is which. Definitely the derived one is the purple one here, I think. It's the last one created. We just saw it? Yeah. It's the derived. And the yellow and the white are bases. So it makes it easier to see what's going on. Maybe next time we can have a look at that. I'll have a look at the way the things are organized. Also, in my printout, should be able to find the thing I just prepared. Where is it? I don't see it. I don't know why. It's something I'll have to fix. What was the thing I fixed? Oh, there's no string here. That's something else. That's perform. That's fine. Just map override. That's something else. Base. That could be. Maybe that's the problem. I don't know. Shouldn't be. It's that list of function table. Breakpoint here. Doesn't do anything. To print out. I don't know. I'll try and figure that out. Okay, see you next time. Sorry, it was just a simple typo. So I just added this on the end. There you go now, see? is what I'm talking about. Here we got the one virtual function table, and eventually we got two. See? This here is some global data associated with one of them. This is global data associated with the base. And eventually it goes back to 1 again when the derived class dies. The vtable list gets reduced. So the derived class must have killed himself. Somewhere. Well, he's purple. Bright purple. I see. It's in the middle of, it's during his destruction. I should print that out after, I guess. The first thing it does is update the global table, indicating that he's dying, and that's what all this extra printf is about. The yellow one. Anyway, all I care about is the fact that that this grows and then shrinks as you go along. It's not printed out in the correct order, maybe. All right, that was it.